Sure. Sure. Great. Great. All right, it's 2:30, so all right, I guess I'll go ahead and get started. So I'm David Hall, and down there is Ignacio. I'm David Hall, and down there is Ignacio. Today we're going to be talking about some of the work natural language processing in Scala. That we've been doing in Scala. This talk is going to have two parts. This talk is going to have two parts. I'm going to talk about the first part of the talk. I'm going to talk about a library that I put together called state-of-the-art sentence level using modern machine learning techniques available and ready to go right now. Available and ready to go right now. And you can use in this talk if you really wanted to. In this talk if you really wanted to. And then after that, Ignacio is going to talk a little bit about some of the research he's been doing. Compositional semantics and how using semantics and how using types is helping him guide that research. Okay. So natural language processing with the Epic Library. Natural language processing. First, I want to talk a little bit about. First, I want to talk a little bit about is involved in natural language processing. Is involved in natural language processing. The kinds of things that we want to do. The kinds of things that we want to do in Epic. So let's consider an example sentence. So let's consider an example sentence like little tiny. Some fruit visionaries. Some fruit visionaries. Someday tumble the red delicious. Could someday tumble the red delicious from the top of America's apple. It certainly won't get there on looks. It certainly won't get there on looks. Now this is an act. This is from an actual newspaper. This is from an actual newspaper. The Wall Street Journal in the 1980s were going to take over every Japanese were going to take over every aspect of American life. And this was another instantiation. By the today. It looks like the Fuji lunch today. It looks like the Fuji did in fact win. Anyway, so given this text, we might be interested. We might be interested in all the phrases in the text. We might be interested in the text. We might be interested in learning the entire syntactic structure and figuring out how the different pieces of the sentence fit together to form a coherent whole. We might also be interested in. How about now? Good. How about now? Good. Okay, I'll try this. Okay. How's this? Okay, how's this? Great. Okay, great. Radiation shield on the walking Faraday cage. Maybe, yeah. I can talk loudly enough to this, but not Test. Okay. We'll just try this. Okay. Okay. Pronouns, right. Pronouns, right. So what does it refer to in this text? So what does it refer to in this text? It's pretty obvious to you and me as native speakers of English, native speakers of English. But it's not clear to a computer at all. Does it refer to the computer at all? Does it refer to the Fuji, America's apple heap, or maybe the top of America's apple heap, or maybe the top of America's apple heap? This is actually a very challenging problem for computers to solve. And there's also a related problem, which is called canonicalization or wickification. And in that, try to resolve the proper nouns to a database. So we want to know that the Fuji refers to Fuji apple, and not to Mount Fuji or Fuji the company or some guy named Fuji or something else. In the Epic Library right now, we support a subset of this. We support the syntactic analysis. We support the syntactic analysis, things like part of speech tagging, as well as things like part of speech tagging, and named entity recognition. And the sort of the little different pieces that you need to make that happen. So. What makes natural language processing challenging? I've touched on this a little bit on the last slide. There's a lot of ambiguity and missing that computers don't have access to. That computers don't have access to. It's a lot of world knowledge that we take for granted that is totally missing computers right now from what we can do. It's a very simple situation I'm in. I might mean a riverbank. Or America, or Bank of America, or maybe even the building. The institution, or maybe even the building. And so we really need to have what's going on in the world in order to really understand what's in text. The other problem is combinatorial structure. Many of these the structures we want to predict in natural language processing. There are exponentially many of them. Based on the input. For parsing, there's order of n to the end. There's order of n to the end. So you have to be careful with your algorithms to make sure that you don't do something naive like enumerate overall full parses. Let's talk a little bit more about ambiguity. In lexical semantics. Where we can see. And I would like to solicit from the audience meanings from the audience if we can do that. So, you made her a duck dish. You made a reduct dish. It's the most obvious one. Yeah, that's a good one.
Yeah, it's the most obvious one. Yeah.
Yeah, that's very good. Yeah, that's very good. You drew something other. You drew something other. What else? What else? Yeah, you did. Yeah, you turn her into a duck. You did. Turn her into a duck. Or turn her into the animal, or duck the. Done either one. Done either one. The other ones that I really like are. You can
This one does work.
Yeah, I've been promised things before. Okay. Right. So with the duck dish, there's actually two analyses. I prepared the duck for her, and I prepared the duck for her, and I prepared her duck, but I didn't necessarily share it with her. Yeah. Okay. Okay. Lots of ambiguity in language. Lots of ambiguity in language. We have to wrestle with every day. The kinds of stuff we have to wrestle with every day. As natural language processing practitioners. Let's talk about a concrete task. That's named entity recognition. Named entity recognition. We want to take a text like this tweet. We want to predict this tweet. People, the organizations, the locations, the other proper nouns that occur in this. So for this, we might identify Adam Goldberg as a person. Shape and East and Churchill Brunei orchards as organization, and Berkeley as organization, and Berkeley as a location, and everything else is not entity in the world. Entity in the world. Okay. Okay. Let's see how we do that in Epic. So first we need to pre-process the document and get it into tokenized and process form. Tokenized and process form system can work with. To do that, we can just take any string. To do that, we can just take a file or URL, and a file or URL can point to an HTML document or a Word document or a PDF, and we'll automatically extract the content. We'll automatically the text out of that document using the text out of that document using the Apache Tika library. Most of the pain of dealing with different formats is taken care of for you. From there, we get a sequence of sentences, each of which is broken up into a sequence of word tokens, including punctuation. And if you're just given a sentence to begin with, you can just tokenize it directly. From there, we can load up the NER. That lives on the class model, and that lives on the class path. And so we just load up the NER model for English. Right now, I only have an NER model for English. Right now, I only have an NER model for English, but soon I'll have German and Spanish, I think. And we can give it a document or a text, a document or a text. Say almost 20 years ago, Bill Watterson walked away from Calvin and Hobbes. We asked the NER model what's the best possible analysis for this, and it decides that almost 20 years ago, Bill Watterson walked away from Calvin and Bill Watterson is a person, did that well. Bill Watterson is a person, did that well. Unfortunately, it says that Calvin and Hobbes is a location. This is actually not totally implausible. If you don't have the world knowledge, because he's walking away from it, and usually you walk away from it, and usually you walk away from locations. But let's say we're not happy with this error. We'd like to fix it. The easiest thing we could do is we could annotate a bunch of data. So we could go out onto Twitter, and pay a bunch of people to annotate the people and the places and the things and the people and the places. So my favorite authors are Jane Austen, Tolstoy, and Hobbes, and that do annotate a bunch of things that look like that. And once we do that, we can load up that data into Epic. With a one-line API call. With a one-line API call, another NER system. You can build up another NER system for your data, trained specifically for your data. You use this thing called SimiCRF. Which stands for Simi Markov. I don't have time to go into exactly what that means today, but exactly what that means today. It's the NER thing. And if we annotated a bunch of data, maybe we'd get the right answer. There are actually other things you can do that tend to be much easier. One option is to use a gazetteer, which is just a fancy word for a big list. Have the same type. So we could go to Wikipedia, and there are tons and tons of these just lists of everything for a given free. for everything, really.
For everything, really.
We can find a list of all webcomic,
we can find a list of all
webcomic or all comic strips.
Calvin and Hobbes is in
And
there.
sure enough, Calvin and Hobbes is in there, and you can pass it into the same API call, and it'll use that automatically and figure out the right figure out the right trade-off between the gazetteer, trade-off between the gazetteer, and then the standard machine learning features has by default. Okay. So that works pretty well. You might have a task where that isn't named entity recognition. That isn't some other task that's related. It's some other task that's related. The features that are tuned and selected, the features that are tuned and designed to do entity recognition may not be the right entity recognition may not be the right machine learning features for you. So in order to build up your own feature set, you need to understand a little bit more. You need to understand a little bit more on how named entity recognition actually works. Named entity recognition breaks up a into a sequence of fields like this, but it also has to annotate every single field. And so the places that aren't, the places that aren't, or whatever your category set is, it's going to mark with another tag. It's going to mark with another tag, usually called outside or other. And we're going to find the best segmentation. Into these typed fields. Into these typed fields. And we're going to say that the best segmentation is defined by the score of each segment. Okay, so how do we get the score? Okay, so how do we get the score for a given segment? Well, it's going to be a sum of feature weights, where the feature weights are properties of that So for instance, we might have a feature weight for starts with another that the first word starts with a capital C. The first word starts with a capital C. Ends with a word that starts with a capital P. Ends with a word that starts with a capital P. And so starts the sentence. This is the kind of declarative specification. This is the kind of declarative specification that we usually think about when we're working in machine learning. Right, a couple other things. And in Epic, we can actually write. Scala using operator overloading. We can actually write something that looks a lot like that. For what features we want to use. For what features we want to use. So we create this thing called a DSL. Which is a domain-specific language. And we import its contents. That gives us access to a lot of identifiers. That allow us to combine features into the set that we want. So, for instance, we can say, give me the first word. Give me the first word. Give me the last word of the span. Give me the last word to what we had. This is very similar to what we had. The word before the begin. The word before the begin. Suffixes. The length of the span. So the length of the span is very. So the length of the span is very. Names tend to be one or two words long. Names tend to be 1 or 2 words long. But organizations might be much longer. Organizations might be much longer, 6, 7 words long. And then, of course, we might have our gazetteer. One of the really great things we can do with this kind of representation is that we can compose features, individual features into larger features. So it might be that using the first word of the last word together, the span and the last word together, than using either informative than using either. And so we can express that using the product operator, and that just works sort of naturally. Okay. So for comparison, this is pretty close to what we actually use in Epic for our near state of the art. I'll actually show you what we use in just a minute. But I want to compare that to what you see in an imperative like the core NLP package from Stanford. And I can't actually fit it on one slide. It's about 1,100 lines of code that look a lot like this compared to that 5 lines of code. And both of them give relatively similar results on the same data sets. So that's nice. And it's really one of the great things about Scala and the kind of compositionality it really enables. Okay. Once we have our featurizer, pass it into the semi-CRF, just like we passed in the gazetteer, instead of the default set of features. Okay. That's it for NER. I want to talk a little bit about constituency parser. We have a constituency parser that works. It uses the same kinds of features. It uses the same kinds of features and the same feature DSL I described for the NER system. But it is a different kind of task. So in this task, we want to figure out who here has diagrammed a sentence before? About a third of you, it looks like. About a third of you, it looks like.
So in that we basically, this is the sort of modern linguistic version of diagramming. We want to figure out where the verb phrases are. We want to figure out where the verb phrases are, and we want to talk about positional phrases. We want to figure out how they attach to one another. We want to figure out how they attach to one another. So as a good example of why we might want to do this, we solve the problem with Scala. We solve the problem. There are two different interpretations of this one. There are two different interpretations of this one. The first is that we solved a problem using Scala. And the second, presumably incorrect. And the second, presumably incorrect, is that we solved a problem that Scala had. And these correspond to two different syntactic parsers. So we solved the problem with Scala. The problem is a noun phrase no matter what. The problem is a noun phrase no matter what. Solve is a verb no matter what. And in these combined right analysis, and in these combined to form a verb phrase. This prepositional phrase attaches to the verb phrase rather than attaching to the noun phrase. Rather than attaching tells you that the with Scala modifies the solving rather than the problem. We can keep composing. Now this might seem like a pretty silly contrived example. But it turns out that a Supreme Court decision from last year rested on a prepositional phrase attachment, just like the preceding one. The president shall have the power to fill up all vacancies that may happen during the recess of the Senate. The question is, during the recess of the Senate, what is that? During the recess of the Senate, what is that? Is it control? The president shall have the power during the recess of the Senate? Or does he have power to fill the vacancies? Or does he have power to fill the vacancies that happened during the recess? And it turns out that it attached to happen rather than to during. As a linguist, I found that really funny. Okay. Anyway, our parser gets state-of-the-art accuracy in 9 languages. I left off English. It's about the same for many of the different data sets in English. But you can see that basically we are the state-of-the-art by a lot, or we're kind of around the same places. We're particularly really good at Basque. Which I don't really understand. We're not quite as good at Arabic. This is a surprise because the NLP community being funded by DARPA, industrial complex, and the military industrial complex cares a lot about the Arabic language. For some reason. Okay. Anyway. So pre-built models, we have models available for all those languages we just listed, except for Arabic and Chinese. I'm having some trouble with tokenization and those languages. We have part-of-speech taggers for all of those languages. Unity recognition for English. We actually have two different versions of depending on what set of tags you want. And we have sentence segmentation that is state-of-the-art and trained on web text and news text. So it works really well on pretty much anything. As well as tokenization that works quite well on English, and works very well on English and most of the other languages that we have models for. Okay. That was a whole lot of stuff about what kinds of annotations we'd like to use in NLP and what we'd like to build. We have a lot of different kinds. We have annotations. We have words, sentences, we have speech tags, sentences, named entities, co-reference speakers, other stuff that I haven't even thought of yet. And all of these annotations have dependencies. In order to find the word boundaries, we need to know where the sentence boundaries are. We need to know where the sentence boundaries are. In order to define the part-of-speech tags, we need to know what the words tags. We need to know what the words are that correspond to the part-of-speech tags. And so there's this big dependency network. That controls what kind of annotations we need before we can build up the next set. So let's try to think of a type-safe way of building a document. So the first thing you would probably think of is you'd have an annotated document type. You'd have an annotated document type that has the content, and something that indicates the words and where they are, as well as the sentences and the past tags. But that's not all you'd need. You also want to be able to get the particular word tag for a particular word, or you'd want to get all the words in a particular sentence. And as you added more and more annotations, you would end up multiplying out these set of annotations exponentially.
These set of methods exponentially.
And what's more, we don't necessarily have those annotations. And so we'd need to use the option type to say whether or not we had those annotations. But again, this kind of gets this solve our problem of wanting to have a Typesafe document type that tells us which kinds of annotations we have. Because we can pass this in anywhere, and it'll just probably throw some kind of exception if you're missing the wrong needed annotation type. So what can we do with this? What we'd like to do is we'd like to say that there's some trait document, some number of annotations. We'd like to have annotation star. We'd like to have annotation star. We'd like to be able to say we have a document. We'd like to be able to say we have a document with tokens and sentences, post tags and parses, and so on. And we'd like to be able to express some typing. And we'd like to be able to express some typing tokens and part of speech tags and parses and part of speech tags. Some type of a document that just has tokens. We'd like to be able to say that. We'd like to be able to say that. In our sort of magical Scala, with type parameters, we'd like to be able to say where we have an annotations method that gives us the annotations for a type T if that annotation type is contained in our list of annotations. Similarly, we can concatenate a new kind of annotation onto a document. Okay. Again, this is what we would like to be able to say. And for the, I think this is the third time this conference someone's talked about this. It turns out that you can get away with using intersection represent exactly this kind of. We can say that a document with sentence has tokens and sentences has tokens and sentences. That is token with sentence with pos tags. And if we use covariance, if we put a covariance annotation, we'll get the subtyping relationship we wanted to have. It's really hacky. I wish there was something better we could do. You could use H-list, but it's not. You could use H-list, but it's not. That's still not quite right either. And actually, these are called slabs rather than documents. But I didn't want to describe that. Anyway, this is what it looks like now. An annotation take T is a super type of annotation. So any super type of annotation that is above that intersection type can be used to pull out the annotation type. We need that type tag to key. The annotations. And it just sort of magically works. So for instance, we can have a parser method that requires a document with sentences and tokens. And it will give us a document with sentences tokens. So we can't pass in a document that just has sentences, but we can pass in a document that has sentences and tokens. But what happens if we pass in a document that has sentences, tokens, and entities? What's going to come out is a document with sentences, tokens, and parses. It's going to magically have forgotten. That's not really what we'd like. So instead, we have this thing called annotation functions. Are very similar to function one. But they have an extra type parameter on that just remembers what the type of the input was. It allows us to remember all the types that we want. It allows us to write our method as something that takes sentences with tokens and parses, even if we pass in something that has tokens and entities, it'll remember the entities and not forget them. What's more, we can actually add composition. So that we can have something that is a sentence splitter, and then tokenizer, and it'll build up a pipeline that says, analysis function that can start with any set of annotations, and I'll tack on sentences, tokens, and parses. So that's it for phase one of the talk. Next up, Ignacio is going to talk about learning semantics with Scala. Go for it.
Thank you. Thank you very much, David. in this second part of David has been talking and presenting these sets of analyzing tools that he has been natural language processing, I think I personally find we are very fortunate that we have available to us in our ecosystem. But especially they are a huge. They are an array of tools for general language. What I'm going to talk about, is in particular to that natural language processing, that deals understanding systems, how we build systems, understand natural language. This is a language. This is a research interest. So this is actually a project. This is actually a project I'm with Professor Christopher Potts there. Computational semantics. I would like to give you a glimpse of how building such a system implies. We try to understand natural language with such a system. We basically utterances in natural language, messages in natural language, and we want to obtain a semantic representation of in natural language. Typically, it could be in natural language, although it could be in another way. What is David? I don't know what it's. There we go. So excuse us. So we have utterances in natural language, and the objective is to obtain semantic representations, actually in a non-deterministic way. All the ambiguities, structural ambiguities, David has been talking about, and that we are going to. So this process is typically known as semantic parsing, although we are going to see right now another version which is interpretive, interpretive. And the way researchers represent this semantic representation, typically use query languages like SQL, or they have been very fruitful results with Lambda calculus, or even programming languages. In our case, we are using Scala. Reasons that we are going to having this semantic representation that is representing the utterances. We can then execute in a deterministic way that and get a denotation in the form of consulting a model, database query, or actually if we are interested on cognitive science, on computational cognition, for example, that would represent the mental speaker, or even in general terms, some kind of world knowledge. So to give you an example, like 1 plus 2, a sentence like 1 plus the semantic representation with the Scala would be something like add 1 and the denotation, the meaning of the sentence, the meaning of the sentence. Another sentence is minus 2 plus 3. David has been interesting because we have two possible denotations. One that way if we parse it that way, or minus 5 if we use this semantic representation. The word crane. The word crane. Ambiguous lexically. So we not only have ambiguity, as we have been mentioning before, but also a lexical ambiguity. So the lexical ambiguity could be, so the semantic representation could be either the noun for a bird, or crane for a bird, for a machine, or for a machine, and so on. So far, so on. Things like 2 is less than 3. Things like 2 is less than 3. For the notation for expression is actually this expression is actually we can have true almost anything. We can have almost anything for a given notation for a given. The sum of 1 to 4. The sum of 1 to 4 representation could be the semantic representation could be something like with a Scala. So with a Scala. So at the core concept that allows us to derive these semantic representations and natural language understanding systems. Natural language understanding systems. A core concept in semantics is known the compositionality principle. The compositionality states that the meaning of a sentence is a function of the meanings of the parts of the meanings and of the way importantly and of the way they are syntactically. So we not only have words, but the meaning of the word combined, but also how they combine. This is crucial. Compositionality principle is attributed to Frege, but this is the formulation by mathematical linguist, who is a mathematical linguist, renowned mathematical linguist. With the compositionality principle, we can understand why all linguists and engineers have several different and actually they are similar. To expressions in the fragment of arithmetic in English are similar in English. Those examples, and the reason is why, the reason for this is the words take a scope. Some of the words take a scope, so we can actually do some bracketing, and get one meaning or the other. For example, in the case of linguists and engineers, if we do this bracket, the resulting meaning of the sentence is actually this group of people composed all linguists and engineers that can be Jan or old. Relation is the same minus 2 plus 3, which has a denotation, right? But we can have also these other bracketing with this group of old people, and a different denotation for their arithmetic sentence, which is minus 5. So as you can see in the trees, we have different trees. We have different versions because they are expressing two different modes, and this is compositional. And this is if we want to build such systems that are language. As a matter of fact, Persilian and Christopher Potts just published some months ago an article where they are proposing a synthesis approach. They are proposing how to learn compositionality, being at the heart of semantics, build such systems. They characterize compositionality. They consider that compositionality characterizes the recursive nature required to generalize to capacity. A creative capacity. So compositionality crucial in language is one of the main reasons why we can be creative. And learning details the conditions. Such an ability can be acquired from data. They are able to propose. That they were proposing that we are able to actually learn compositionality by using machine learning traditional, which has been for several years an ongoing effort in understanding. However, you can imagine that if we want to learn from uterances, semantic representations, we want to learn from those and derive the denotation. It is actually very expensive. Building a semantic representation is complex. It requires annotating data. This is a very daunting task. When he was actually working at Berkeley in David's group, he proposed a couple of years ago a very interesting new approach to this problem. Actually considering that we can learn from utterances and answers. The logical forms are latent variables in this. And this is important for the reason that these pairs of utterances and answers appear naturally in our So if utterances are, let's say, state with the largest area, it is very common to find answers. It is very common to find answers using whatever corpus you are using. Instead of the complex tree that represents semantically the logical form of a state. You can imagine questions like Brad Pitt, the movies where Brad Pitt is the main character. The answer here instead of just building a huge logical form that is very difficult for professional linguists to. So with this idea, making them actually understand natural language, considered to be a structure prediction problem for pieces. First one is an initial grammar that we are going to refine during the learning, because I'm going to explain why this is the case. So from the examples we saw before, -3, we know what +3, we know what 2 and the meaning of those words, and the meaning of those words. Actually, for a machine, when a machine is trying to learn those utterances, what is seen is something like this. Is someone familiar with this? That's great. That's great. We have to talk later. No, it's interesting because I think there are more people in this room experts on Maya writing in the world. So that's great. So this is Maya writing. So that's great. This is Maya writing. This is what a machine actually sees. I can tell you this is representing summation. So if we happen to have this example and then the denotation, which is 5. What we are doing by generating is actually the grammar is actually providing for a given logogram here a little bit. We are simplifying here a little bit and telling you that this is the function. Providing this logogram with the possible values of this head with all the possible variants for numbers, and the same with this. So with the hope that by seeing more examples with another denotations, we can start refining. So we can the grammar. To say, well, we can. This is 5. Well, I mean, it has this 5, and it has this 1 and this 1 here. This has the same 6. Maybe well, 6 could maybe well, this could be. We can start doing hypotheses. This is actually how decipherment. And this is actually how decipherment. But we want to do this with machine learning techniques. Machine learning techniques. Of the day, we are over generating and with the converging to a solution where logogram, which is actually to be read shock, which is actually to be read classic Mayan is something like count or sum. This is the actual value for add. That value for add. That head for 4. That one for 1. That one for 1. 2 and the rest 2 and the 6. So we are considering that the machine is understanding by learning the lexical items and the way they combine together. So once we have this initial grammar that we are going to refine during the learning, devise some feature representation. We need an objective function. We need an objective function, an algorithm for optimizing the objective function. So I'm going to show you how we can do this in a succinct way, in a concise way with Scala. So actually we start by we use the GLL library by Combinators Parser library by Daniel. We are very grateful. It's a piece of with software. The combinators, we are basically providing this over-generating for every initial grammar, for every possible symbol in utterances. We are providing all the possible here, semantic representations here, and for every lexical item, we are providing all the possible combinations of representations. So you can once we parse with this initial grammar, we are trying to replace failure with a stream of success, but the stream is actually because we have a huge stream, because we have lots of possibilities. While we are doing the parsing, we are at the same time building an abstract syntax tree. This algebraic with this algebraic that are basically a combination of some types. So we build types. So we build based on these utterance. We build the abstract syntax tree. And interestingly, if we consider this as the initial algebra, it can be also considered as a carrier for a functor that goes from a category of utterances to the category of meaning. So at the end of the day, this abstract syntax tree. From the utterance, we can destroy the abstract syntax tree by folding it, catamorphism, and obtain the denotation, the utterance with this single operation.